In a three-phase, four-wire circuit where all loads are connected phase to neutral, determining the neutral current is crucial for ensuring safety and proper system operation. The neutral wire carries the imbalance of current between the phases. To calculate the neutral current, we'll explore both a straightforward calculation and a field method. The most direct method involves summing the current in each phase. The formula is neutral current equals phase current A plus phase current B plus phase current C, using the provided example, where phase is 5 amps, phase B is 10 amps, and phase C is 15 amps. The neutral current is calculated as follows. Neutral current equals 5 amps plus 10 amps plus 15 amps, which equals 30 amps. This simple addition provides the total current flowing through the neutral wire. Now let's discuss a field method for quickly estimating the neutral current. The field method relies on the principle that in a balanced three-phase system, the neutral current is approximately equal to the square root of 3, which is approximately 1.732 times the line current. To use this method, measure the current in two of the phases. Since it's implied that the circuit is balanced, the third phase current is assumed to be similar or the same. So, with the example currents of 5 amps, 10 amps, and 15 amps, we would use the sum of all three. The formula for this method is neutral current equals the square root of 3, approximately 1.732 times the load current. In this case, load current refers to the total current in one phase. However, in an imbalanced system, you would need to include all the phases, so it's the sum of each phase's current. Using the provided values, neutral current equals 1.732 times 5 amps plus 10 amps plus 15 amps, which simplifies to 1.732 times 30 amps, which equals 30 amps. This field method provides a quick estimate without needing precise measurements from all three phases individually. The more general formula for calculating the neutral current in a three-phase, four-wire system is neutral current equals the square root of 3, which is approximately 1.732 times the load current. Here, load current represents the total current flowing in one phase. This formula accounts for the phase relationships in a three-phase system, providing a more accurate result, especially when the loads are not perfectly balanced. Now let's address a few practical considerations. Firstly, wire sizing. It is essential to select the correct wire size for the neutral conductor based on the calculated neutral current. According to the National Electrical Code, or NEC, the neutral conductor must be sized to safely carry the maximum expected neutral current. Using a conductor that is too small can lead to overheating and potentially cause a fire hazard. Secondly, breaker sizing. Each phase in this example is protected by a 20 amp circuit breaker. It is important to ensure that the circuit breakers are appropriately sized to protect the conductors from overcurrents. If the loads were to increase significantly, exceeding the breaker's capacity, the breaker should trip, preventing damage to the wiring and equipment. Thirdly, continuous loads. Since all loads are assumed to be continuous, the NEC requires that the overcurrent protection device, such as the circuit breaker, be rated at not less than 125% of the continuous load. This is to account for the sustained heat generated by continuous operation. In this scenario, the 20 amp breaker should be sufficient, provided the actual continuous load on each phase does not exceed 16 amps, which is 80% of the breaker's rating. Now let's consider the implications of an unbalanced load. An unbalanced load occurs when the current draw on each phase is not equal. This situation is common in many electrical systems, especially in commercial and residential settings where single-phase loads are distributed across the three phases. The greater the imbalance, the higher the neutral current. High neutral currents can lead to several issues. Firstly, increased energy losses. A higher current in the neutral conductor results in increased resistive losses, which means more energy is wasted as heat. This can lead to higher electricity bills and a less efficient system. Secondly, voltage drop. Significant neutral current can cause a voltage drop along the neutral conductor. This voltage drop can affect the performance of voltage-sensitive equipment connected to the circuit, potentially leading to malfunction or damage. Thirdly, harmonic distortion. Nonlinear loads, such as electronic devices and LED lighting, can introduce harmonic currents into the electrical system. These harmonic currents often flow in the neutral conductor and can exacerbate the issues caused by unbalanced loads. To mitigate the effects of unbalanced loads and harmonic currents, several strategies can be employed. Firstly, load balancing. Distribute the single-phase loads as evenly as possible across the three phases. This minimizes the current imbalance and reduces the neutral current. Secondly, K-rated transformers. Use K-rated transformers, which are designed to handle the additional heating caused by harmonic currents. These transformers have a high capacity for dealing with harmonic distortion. Thirdly, harmonic filters. Install harmonic filters to reduce the level of harmonic currents in the system. These filters can be placed at the load or at the service entrance. Fourthly, oversized neutral conductors. In situations where high neutral currents are unavoidable, consider using an oversized neutral conductor. This reduces the resistance of the neutral path and minimizes voltage drop and energy losses. Let's talk about using a clamp meter in the field. Firstly, safety precautions. Before taking any measurements, ensure that you are wearing appropriate personal protective equipment, or PPE, including safety glasses and gloves. De-energize the circuit whenever possible before making any connections. Secondly, selecting the right clamp meter. Choose a clamp meter that is capable of measuring AC current and has an appropriate range for the expected current levels. A true RMS, or root mean squared, meter is recommended for accurate measurements, especially when harmonic currents are present. Thirdly, measuring phase currents. Clamp the meter around each phase conductor individually to measure the current flowing in each phase. Record the readings for each phase. Fourthly, measuring neutral current. Clamp the meter around the neutral conductor to measure the neutral current. Ensure that you are only clamping around the neutral conductor and not any other conductors. Fifthly, interpreting the readings. Compare the measured phase currents to the calculated neutral current. If the measured neutral current is significantly higher than expected, investigate potential causes, such as unbalanced loads or harmonic distortion. Sixthly, documenting the measurements. Keep a record of all measurements, including the date, time, location, and circuit being tested. This documentation can be useful for future troubleshooting and analysis. Now let's discuss troubleshooting high neutral current. Firstly, identify the source of imbalance. Use a clamp meter to measure the current in each branch circuit to determine which circuits are contributing to the imbalance. Secondly, redistribute the loads. Move some of the loads from the heavily loaded phases to the lightly loaded phases. This can often be accomplished by simply moving appliances or equipment to different outlets. Thirdly, check for faulty equipment. Inspect all equipment connected to the circuit for signs of malfunction or damage. Faulty equipment can draw excessive current and contribute to imbalance. Fourthly, verify wiring connections. Ensure that all wiring connections are tight and secure. Loose connections can cause voltage drop and increase the likelihood of harmonic distortion. Fifthly, consider adding dedicated circuits. For high-demand loads, consider adding dedicated circuits to reduce the overall load on the existing circuits. Sixthly, consult with a qualified electrician. If you are unable to resolve the issue yourself, consult with a qualified electrician. An electrician has the expertise and equipment to diagnose and repair complex electrical problems. The NEC provides specific guidelines for neutral conductor sizing and overcurrent protection in three-phase systems. Article 220.61 covers the calculation of the neutral load for feeders and services. This section provides detailed instructions on how to determine the maximum neutral current based on the type of loads connected to the system. Article 310.15 addresses conductor ampacity and provides tables for determining the allowable ampacity of conductors based on their size, insulation type, and installation conditions. It is essential to consult these tables to ensure that the neutral conductor is adequately sized for the expected current. Article 408.21 covers the requirements for neutral busbars in panel boards and switchboards. This section specifies the minimum size and rating of the neutral busbar to ensure that it can safely carry the maximum neutral current. Let's discuss the importance of proper grounding. Proper grounding is essential for safety and proper operation of any electrical system. The grounding system provides a low impedance path for fault currents, which helps to trip circuit breakers and prevent electrical shock hazards. The NEC requires that all electrical systems be properly grounded in accordance with Article 250. This article provides detailed instructions on how to establish a grounding system, including the use of grounding electrodes, grounding conductors, and bonding jumpers. A properly grounded system helps to minimize the risk of electrical shock, reduce the likelihood of equipment damage, and improve the overall reliability of the electrical system. Let's also discuss the role of surge protection. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges and spikes. These surges can be caused by lightning strikes, utility switching, or other transient events. SPD work by diverting the surge current to ground, thereby protecting the connected equipment from damage. The NEC recommends the use of SPD in all electrical systems, especially those that are sensitive to voltage fluctuations. SPD can be installed at the service entrance, at the panel board, or at the individual equipment location. Using SPD can significantly reduce the risk of equipment damage and downtime due to voltage surges. Let's look at energy efficiency. Implementing energy-efficient practices can help to reduce energy consumption and lower electricity bills. There are many ways to improve energy efficiency, including using energy-efficient lighting, installing programmable thermostats, and upgrading to energy-efficient appliances. Another effective strategy is to conduct an energy audit to identify areas where energy is being wasted. An energy audit can help to pinpoint inefficiencies and recommend specific measures to improve energy performance. Additionally, consider using power monitoring equipment to track energy consumption and identify potential problems. Power monitoring can provide valuable insights into how energy is being used and help to identify opportunities for improvement. Let's talk about the benefit of regular maintenance. Regular maintenance is essential for ensuring the long-term reliability and safety of an electrical system. A well-maintained system is less likely to experience failures, which can lead to costly downtime and repairs. Regular maintenance should include inspecting wiring connections, testing circuit breakers, and cleaning electrical equipment. It is also important to keep accurate records of all maintenance activities. These records can be used to track the performance of the system and identify potential problems before they become serious. Additionally, consider using a preventative maintenance program to schedule regular inspections and maintenance tasks. A preventative maintenance program can help to extend the life of the electrical system and reduce the risk of unexpected failures. Now let's discuss safety standards. Adhering to safety standards is crucial for protecting people and property from electrical hazards. The NEC provides a comprehensive set of safety standards for electrical installations. It is essential to follow these standards carefully to ensure that the electrical system is safe and reliable. In addition to the NEC, there are other safety standards that may be applicable depending on the specific application. These standards may include those developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to stay up to date on the latest safety standards and to follow them diligently. In summary, calculating neutral current in a three-phase, four-wire system is essential for safety and proper system operation. Understanding the formulas and methods for calculating neutral current, along with the practical considerations discussed, can help to ensure that the electrical system is operating efficiently and safely. Always adhere to safety standards and consult with a qualified electrician when needed.